Welcome to Spring LIB.
For this problem on the topic of electromagnetic induction, we are given a long straight solenoid with a cross-sectional area that is known, as well as the number of turns per unit length. We also know the current that is carried in the windings, and we are then told that a second winding of given number of turns encircles the solenoid at its center. The current in the solenoid is then turned off so that the magnetic field of the solenoid becomes zero in a given time. We want to know what the average induced EMF in the second winding is. Now we know that in the magnetic field of a large straight solenoid is equal to B, which is mu naught N times I, where N is the number of turns per unit length and I is the current in the windings. We also know the magnetic flux is the magnetic field B times the cross-sectional area A, and we are given the cross-sectional area in this case. Now we know to solve this that the average induced EMF is equal to the number of turns N times the rate of change of magnetic flux, delta phi, by delta T. And we can write this as N, and remember the change in flux is the area times the change in magnetic field, which is the final magnetic field, minus the initial magnetic field. That gives us delta B. And all of this in a time of delta T. And again, we can write the magnetic field using the equation above. So that's Na times the magnetic field, which is mu naught N I. And all of this divided by delta T. Now, since we know these values, we can calculate this average induced EMF in the second coil. That's mu naught, which is 4 pi times 10 to the minus 7 in SI units, times the cross-sectional area of 12, or actually the number of turns, 12, times the cross-sectional area of 8 times 10 to the minus 4 square meters, times the number of windings per unit length, which is 9,000 per meter, divided by the current which flows through the windings of 0.35 amperes all over the time of 0.04 seconds. So calculating, we get the average induced EMF in the second coil to be 9.5 times 10 to the minus 4 volts.